Assalamualaikum and good day. As promised, as I have promised that I will prepare a mixed lecture for the velocity analysis. On the last class, I have not completed all the examples that on the slide. So today, I will basically continue on. Okay, we have done a saving machine and this one. Now we're going to address point of floating link and also hinge mounted cylinder linkage. Okay, then let's move on to the slides of interest. Okay, we have done this. Okay, done this. Done this. Done this. Done this. Done this. Done this. Okay, we haven't done this yet. In this case, if you refer to the previous slides, it is exactly the same except for the addition of this part, which is point E. Now, if you want to find point VE, then we need to follow slightly different way. Okay. Okay. Now, link AB is rotating clockwise at 15 RPM. Rotating clockwise, that means which is in this way, this direction. So what is the velocity of point E? So we need to find what is point E. The easiest is really that point to find the relative velocity of E with respect to B. Okay, the point E is on the link BC but not on the line connecting B and C. Okay, it is offline. So previously you already defined what is VCB, so we can use this part, but now this is not in line with this. No, it is not. Okay, let's just delete first. So omega CB is equals to 0.79 radian per second. I think this is coming from the previous one. VE is equals to VB plus VEB. Okay, we know the VB. Now we need to find what is VEB. VEB is actually, the velocity of EMB. How to relate that? Now, we have to create a straight line between B and E. Okay. Next, we can find the velocity of EB, which equals to omega CB times REB. Okay. Omega CB here. Remember, this is velocity. This is basically rotational speed, like this. So rotational speed of angular velocity of BC and BE will be the same, right? So if you want to find VEB, in this case this is something like this, VEB, it will still depend on the same angular velocity of omega CB. So therefore, you can find out that VEB is equals to 0.79 times 40, which is from this part, which is coming from the distance between B and E, and we got the VEB equals to 31.6 millimeter per second. So this is VEB, right? So next, so this VEB is at 76 degrees to horizontal. In this case, it will be something like this. Okay, so sorry, no, like this. This is 76 degrees. How do you want to find that? Well, basically, you need to create a horizontal line. And how to do that? Well, you can find between the angles here and here and so on relative to the actual horizontal line here. Okay. So now this is at 76 degrees, and of course we have to measure it here to 31.6 millimeter per second. So now, so VE is equals to VB plus VEB. Then we can draw the straight line here, and then we measure it. So by measurement, we got V equals to 38 millimeter per second at 8 degrees to horizontal. Okay. If we measure the straight line here, it should be 8 degrees. Okay, so we have done this. So basically, in order to find VE, you need to find VEB. You need to be based on VEB. Okay. And then this is depending on the angular velocity of VBE, or which is also equals to omega CB. Sorry, omega, in this case basically, sorry, omega EB is equals to omega CB, right? Because it is rotated at this, is at the same point here, point B. Okay, so we'll move on next to the next example. For velocity of a point on a floating link of a 4-bar linkage. Right? Okay, what's the problem here? The stem stems on the impact and then stem on the board repetitively as the crank rotates. So this is the cranks that rotate. Okay, we don't know yet. I don't know yet which direction it will be. The crank, floating link stem. Okay. So what's the question now? So we draw the kinematic diagram. Right. So X is basically the point of interest. Right. So we can have a kind of triangle like this. Join A, B, C, and D. So link 1 is rotating clockwise at 20 rpm. What is the velocity at point X? Okay. What is the velocity at point X here? And this is rotating 20 degrees clockwise. 20 rpm, 20 rpm. Okay. So what is the velocity at X? Okay, move on. So VC equals to VB plus VCB. Okay, we know that. So we plot VB. Then we plot also VC. Okay. Then we need to find which direction will be of VCB. Okay. So in that case, we have to plot of VB and VC plus first. Okay. And for Vx, is equals to VB plus VXB. Okay, VB plus VXB. So VXB is basically this straight line. So this is the straight line of VXB. Okay. So now we don't know the direction, both direction of it, which direction will be of VXB. Okay, and of course Vx equals to Vc plus Vxc. Okay, Vxc is in this direction. Okay, Vxc. So can find the relation here. So C rotates about D. The velocity direction is known. X rotates and translates at the same time, thus the velocity direction is unknown. So first, must first determine BC before we can determine BX. So this is all relative now. So what will be the next step? Next method. Okay. VC equals to VB plus VCB. Omega 1, 20 RPM clockwise. So it will be in this direction. So it's equals to 2.09 radian per second clockwise. 1 VB is equals to omega 1 RBA equals to 6.79 inch per second. So VB will be in this direction, okay, at 30 degrees to horizontal. So it will be 30 degrees like this, okay. So we can draw. Of course, we have to measure it. Maybe in this case, maybe 3.69 inch. Hey, no, sorry. 6.79 inch. 6.79 inch. Okay. VC is equals to, so we know VC, this is of course 90 degrees. Okay. Draw a straight line there. So VCB is in that direction. Okay, 90 degrees to this part, CB. So we know that this is of course the original position. So VC will be in this direction. VCB will be in this direction. So by measurement, we need to measure the angle here, of course. What is the angle here? And what is the angle here? So in this case, VC is equal to 3.85 inch per second at 72 degrees to horizontal. And VCB is equal to 4.75 inch at 1 degrees to horizontal. So Vs is equals to Vb plus Vxb. So we move on. So Vxb is, it is 90 degrees to this part, to xb, right? Okay, it's not in this diagram, it's not being drawn exactly at 90 degrees, but no matter. So draw a line from the end of the vector VB, and the line is perpendicular to Vx. Okay. Where is it? So Vx equals to Vc plus Vxc. Okay. Vxb. Okay. Of course, we need to measure this according to horizontal. Then we can reflect it to this line VXB. Okay. So Vx also is equal to VC plus VXC. which is xc equals to 90 degrees to xc. Okay. So now we draw another line from the end of vector VC. So this line is drawn perpendicular to CX. So almost 90 degrees, but it is not. Okay. So the intersection is the endpoint of the vector Vx, which start at the same point as VB and VC. Okay. So VXB and VCB. So VXC is in that direction. So therefore Vx is this line here. Okay. So both will give the same result actually. You can actually solve independently, not really depending on VXC or VXB only. So you can solve by VB plus VXB, or you can solve by Vx equals to VC plus VXC. So you do not need to do both actually. You do not need to do both. Either one will be okay. Okay. So measure the length and the angle vector Vx. So Vx equals to 1.1 inch per second at 8 degrees to horizontal. So this is 8 degrees. Okay, done. Now this is to find a velocity at a point of interest x. Okay, move on. So then what is the omega 3? Will be Vc over R, Vc equals to RCD, CD, okay, the angular velocity here, either counterclockwise or clockwise, but in this case, since Vc is on this direction, then it will be counterclockwise, CCW. In this case, Vc divided by RCD, 3.85 divided by 6.75 inch, 0.57 radian per second. Omega 2 VCB over RCB, VCB, so 4.75 divided by 9.38, the length of the link BC, equals to 0.51 radian per second. So VXB is equals to, okay, now to you can find now VXB, you can find the value of VXB equals to omega 2 plus times RXB. So in this case, omega 2 clockwise, this is omega 2, so omega xb also will be in the same direction, same omega 2. So Vxc equals to omega 2 times RCX. So we got 3.1 inch per second. Vxb equals to 5.6 inch per second. Alright. So we have got all the values now. Now there's another example, which is I hope this is the last example, which is velocity analysis of a hinge mounted cylinder linkage. So we're going to study the velocity of the hinge here, okay, since it will be moving in this direction and also in this direction. So it's a combination direction. So if you look at the motion here, it's not as simple as normal. Okay, this is the kinematic diagram of the hinge cylinder linkage. So this is the coincidence point. We're going to analyze on point B here. Joint B represent the identical location of 2 points on the 2 different links, identified as B2 and B4. The points are coincident at the particular instant of time only as the linkage moves. So point B is on link 2 rotating about A, move perpendicular to link 2. So we have a velocity that is perpendicular to BA, right? This is perpendicular. Next, point B4 is on link 4, rotating about C. So, which is moved perpendicular to link 4. So we have another 90 degrees here, right? Then point B is also sliding relative to point B along link 4. So that means we go along the line here. We go down the line here. So VB2 B4 is parallel to 4, parallel to link 4. Then we have, so VB2 is equal to VB4 plus VB2 over VB4. So this will be the relationship. Now we have to start to sketch it. Now VB2 is perpendicular to 2. Okay, we don't know yet in which direction it will be. And VB4 is perpendicular to 4. Right? 2 degrees there. So with that, we can start to draw exactly. Okay, VB4 and VB2 we can consider as an absolute velocity at the moment. Okay, at the moment, not yet. So it is originating at one single point, if you remember. Okay, sorry. I cannot reverse. Oops. Okay. Then we have a last example here, which is hydraulic driven platform. It's given a platform here, which is this is the platform. Okay, this is the platform, which is carrying a box moving from this to another platform. Okay, so this is why it's connected to two linkages, one side here and another side here. If you remember, this is the 4-bar linkage system. Okay, the platform S1, then we have the bar there, and so on. Okay, so these links connected to the hydraulic cylinder. So what happened that okay, I'm not sure whether it's going from higher platform to the lower platform or on the other side. Anyway, let's move on. Extend, that means it's bringing from the top platform to the lower platform. So the hydraulic cylinder extend at a speed of 16 feet per minute. Determine the velocity of the platform at this configuration. So we want to know the velocity of the platform here, where it moves. Okay, how to determine that? Okay, it is extending at 16 feet per minute. This is the platform. So first we designed the numbers and the alphabet for joints and the links. Always take the velocity of the piston relative to the cylinder. Okay, so now it's 15 feet per minute. It's on the left direction, parallel to link 2. So we draw one line there. Okay, so this is VB4 over VB4 relative to B2. Okay, B4 relative to B2. VB4 equals to VB2 plus VB4 relative to B2. So this is VB4, vertical line. Okay, so now we know that VB4 is the results of VB2 plus VB4 relative to V2. Okay, so this will be in this direction, but later on we're going to do that later on. Next, then this is VB4, this is VB2. So in this case we do not know the direction yet. Either will be up or down, so which one? But we can see from here, right, where in this direction when we draw, it will be somewhere here. Okay, oh sorry, not exactly there. Okay, it will be in this direction. Of course this is 90 degrees. Okay, this is 90 degrees to link to, so that's a VB2. So now we have to just measure it, VB2. Then we'll be able to measure VB4. So by measurement, VB4 equals to 18.8 feet per minute. VB2 we measure, we got 10 feet per minute. So omega 4 equals to VB4 over RBA. So if you know this link, RBA, so then we'll be able to find omega 4. So in this case it is 5.37 radian per minute counterclockwise, which is in this direction. Okay, now we'll be moving in this direction, omega 4, right? So next, VC equals to omega 4 times RAC. So RAC is this, RAC, the radius of this between A and C. So VC is equals to the 5.37 times 5.3, the length of AC. So it's equivalent to 28.5 feet per minute to 20 degrees. Horizontal. So basically, this VC is the velocity of the platform. Okay, so basically even here also will be the same, VE and so on. Okay, in this case the VC is the velocity. Okay, I think that's all for the example of velocity analysis. Hopefully inshallah I will continue with the acceleration analysis later on, very near to the future. Thank you very much. Assalamualaikum. Bye.